I'm really grateful to the organizers for giving me a chance to speak here. I'm not at all a specialist in the subject of my talk, in the approximation theory. It's rather a byproduct of what came out of our research on Hankel operators, and an opportunity to present this to such an impressive audience of specialists is really, really important for me. Thank you very much. So, first of all, before I forget, I should say that this is a joint work with Dmitri Yafaev from Rennes. And it is possible that some of you have heard a version of this talk in his rendition. I don't know. Okay, so I will speak about very simple things, really. Let me start with a very gentle warm-up. I will start with a polynomial approximation. And okay, so Pn will be the set of all polynomials in one variable of degree less than or equal to n. And let me start by a very simple thing. So we'll look at a certain interval, let's say -1, 1, and let me state the Weierstrass theorem in terms of polynomial approximation. Okay, so as I said, it's a very simple talk. Okay, so here in one direction, it's a consequence of the fact that, so omega is a function, right? So in one direction, it's a consequence of the fact that the uniform limit of continuous functions is continuous. In the other direction, this is the Weierstrass approximation theorem. Now let me state the quantitative version of this theorem, which is the Jackson-Bernstein theorem. Okay, so as I said, many people here know this far better than I, but still let me explain. So Jackson-Bernstein theorem says that the rate of approximation of a function by polynomials, by algebraic polynomials of degree n, behaves like 1 over n to the power alpha. Here alpha is a positive number. If and only if this function belongs to the class C alpha. You have to be a little bit careful for integer alphas, because for integer alphas this is not the Hölder continuous functions, this is the corresponding Zygmunt class. Okay, so now let me remind you the theorem due to Bernstein again. So I think the original version was 1913. he published 2 papers on this, 1913 and 1938. So he considered a specific example of a function in the class described above. Okay, so we take a function in that C alpha class, and we look at how we want to get a more precise information about the rational approximation of that function. So he proved the following, that the rate of approximation is precisely n to the power alpha, and there is a constant here, positive constant, only alpha must be not an even integer, of course. For an even integer, this is a polynomial in itself, and so you get nothing interesting. So there is an interesting story related to this constant. This is called the Bernstein Constant. B of 1 is approximately, let me copy it from here, 0.28, and which is close to the value of 1 over 2 over root of pi. And Bernstein speculated that the value of this constant is exactly 1 over 2 root pi. But then in 1980s, Varga and Carpenter disproved this conjecture numerically by computing this constant more precisely. So it's not equal. It's approximate, but not equal to. Okay. So yeah, and the values of these Bernstein constants are still not known as far as I'm aware. Even for alpha equals 1, and for more general alphas, there are alternative descriptions, but it's not even known whether they are rational or irrational. Okay. So this is sort of a warm-up to the topic of my talk, rational approximation. So theorems of this type are called constructive approximation theory, where you are describing a certain class of functions in terms of the speed of convergence of approximations to this function. And theorems of this type are called maybe theorems about best approximations, where you take a particular model function and you look at the exact rate of approximation of this model function. So I'm going to be talking about the second problem, okay, about approximations of some particular functions. So if you ask me how to motivate, why would you want to compute constants like this, it's maybe not such an easy question. I'm not a specialist, but to me, it's maybe there are 2 motivations. First, it's a good sport, okay, to try to compute these constants. And secondly, of course, the interesting aspect is not upper bounds in such things, but lower bounds, because lower bounds tells you the limit of how fast you can hope to approximate something if you stick to a certain method of approximation. Okay, so as I said, this was a warm-up. Now let me start talking about rational approximation. So now I'm talking about rational functions, which are functions of this type, polynomial over a polynomial, and the degree of both numerator and denominator are bounded by n. As far as I'm aware, very early in the history of rational approximation, there was maybe an opinion that rational approximation works pretty much similar to polynomial approximation. After all, if you look at this set of functions, they have, roughly speaking, 2 n parameters, where polynomials have, roughly speaking, n parameters, and one wouldn't think why rational approximation would work radically different from the polynomial ones. But the first result that kind of changed this opinion was in the 1960s. Newman proved the following. He looked at the rational approximation of exactly this function. More precisely, he even looked at alpha equals 1. So he looked at the distance in L infinity minus 1, 1. Of just absolute value of x to the rational functions. And he proved that the rate of convergence to 0 is actually exponential. Okay. And this was the first indication that actually the rate of convergence, that rational approximations work much, much better than polynomial ones. So then, after many, many contributions by several authors, Stahl sort of finished the job here in 2003. He provided the following sort of final answer to the question of how do these rational approximations behave. Let me copy it from my sheet. So he considered general powers alpha. So here alpha is positive. Okay, so this is Stahl's result. He got an explicit constant. It is interesting that although in the simpler problem of polynomial approximation, the exact value of the constant is not known, in a more difficult problem of rational approximation, Stahl got this constant. Yeah, I should actually mention that the major difference between these two types of approximations is that rational approximation is nonlinear. The set of rational polynomials of degree n is nonlinear. If you add two rational functions of degree n, you get, in general, rational function of degree 2n. Right? It's a very nonlinear problem. So, anyways, this is what Stahl obtained. And by the way, it's clear that when alpha is an even integer, the right-hand side disappears, which is not surprising, right? For an even integer, you get exactly a polynomial function. Okay. So the aim of my talk is to give a result in the similar spirit, but we want a power convergence here instead of the exponential convergence. So I will discuss a rational approximation of a particular explicit model function for which you get power convergence like in Bernstein's theorem, but for rational approximation. Okay, let me write this down. Okay, so aim for some explicit function which I denote omega alpha. I will write it down in a few minutes to obtain the following type of result. Okay, so we look at rational approximation. And we get an exact constant, which I will compute, but power rate of convergence. So there are two caveats to this. So first of all, first is a minor technical one. instead of working on the unit interval, as in these results, I will work on the unit circle. This is a minor technical point. So I will work on t, not on -1, 1. And so in my case, the function omega will be the function of the complex variable of the absolute value 1, and the corresponding rational functions will also be rational functions of z. So effectively, if you are thinking of the unit circle as an interval -pi to pi, we will be approximating by trigonometric rational functions rather than algebraic rational functions. So that is one difference. But another difference, which is more seriously, we will approximate in the BMO norm, not in L-infinity norm. Okay? And this is something which is absolutely essential for what we are doing, because our results are a consequence of the Adamyan-Arov-Krein theorem, which relates the distance, such distances in the BMO norm, to singular values of Hankel operators. And I will talk about this a little bit later in much more detail. For now, I'm just indicating the nature of these results. Okay, so actually the fact that we are dealing with the BMO norm is not so surprising. So let me just quickly remind you that in many questions of harmonic analysis, BMO is a proper substitute for L-infinity, right? So while L1, the dual space to L1 is L-infinity, the dual space to the Hardy space H1 is the space of analytic functions in the BMO space. And that's why BMO turns up in our problem. So I should also specify which norm do I set in the BMO. So in the BMO, if you look at many sources, there are as many as maybe more than 10 possible ways of introducing norms in the BMO space. And because we are in the business of computing the asymptotics, we have to specify exactly which norm we're having, right? If you change the norm to an equivalent one, of course, this will change the situation here. So for us, this is the definition of the BMO norm, essentially, right? We are dealing with the norm induced by this duality. Maybe I should be a little bit more specific. So this norm, this duality gives you the norm only on the BMO A, the analytic BMO functions, right? So what we do in general, let me write this down. So if you have a function on the unit circle, by definition, our BMO norm is defined like this. Okay, so we split the function into the analytic part and the anti-analytic part. By complex conjugation, anti-analytic part is mapped to an analytic function, and then we simply take the maximum of these two BMO-A norms. And BMO-A norm is precisely given by this duality.
This is a conformally invariant form of the norm with the Poisson-Kernel?
I'm out of my depth here, I have to say. Yeah. I don't know. I'll have to think about it. Yeah. Okay. So yeah. So now I'm almost ready to state the theorem. The only thing I need to say is to describe the function omega alpha that we're dealing with. Okay, so send this up. So I need to define the exact function that my results pertain to. And you shouldn't be surprised if I tell you that this function is logarithmic. It has a logarithmic singularity. Indeed, you see, if you take a power function, then Stahl's theorem tells you that you get an exponential rate of convergence of rational approximations. So to get a power rate, you have to go much worse. You have to go logarithmic. Okay? So more precisely, this is the definition of my function. Sorry, 1 minus alpha. This is the function. Okay? So this is the behavior of this function near theta equals 0. Now, unfortunately, when theta equals 1, you get another singularity, and I want to remove this, so I simply multiplied by a certain smooth function. Okay, so theta here is between minus pi and pi, and this chi naught is just a smooth cutoff function. It is 1 near 0, and then it smoothly goes to 1, so it cuts off the undesired singularity of this function as theta equals 1. Okay? So remember that BMO space is very close to L infinity, but it's a bit larger than L infinity, and in particular, functions in the BMO space are allowed to have mild logarithmic singularities. So precisely singularities of this type. So omega alpha is in BMO precisely for alpha greater than or equal to 0. And in fact, we will be interested in the VMO case. This is when you have convergent approximations, and this corresponds to alpha being strictly positive. Okay. Okay, so now I'm ready to state the main result. Okay. For any positive alpha, the distance in the BMO norm between omega alpha and the rational functions of degree n converges to an exact constant, explicit constant. Okay, so this is the constant. This is the beta function. Okay, so there is, as far as I'm aware, there's nothing especially significant about the value of this constant. I've just written it down to show that it's explicit. You can compute it. So that's the result. Okay, so I've given my main result. I'm good. The rest will be just commentary. Okay, commentary to this. So some remarks. First of all, it's a kind of trivial remark that if alpha equals 1, then the right-hand side disappears because of this, which is not surprising because for alpha equals 1, this term disappears and you just are left with this smooth cutoff function. Okay, so that's clear. So next, if alpha is greater than 1, then this function omega alpha is actually bounded. And you can ask a question about the rational approximation in the L infinity norm. Okay. So in this case, as far as I'm aware, the question of the asymptotics is wide open. But there are upper and lower bounds in terms of this power. So let me write this down. And in some form, they're due to Gonchar from the 60s, although Gonchar had some logarithmic term here, and then Pekarsky had this. So he considered this as a kind of, this function as a kind of example in his other work on constructive approximation. Okay. So finally, let me say that this is a very simple, very small sample of our results. And in fact, we have similar results for a more general class of functions. So let me introduce a sort of analog of this omega alpha, which I will call omega alpha plus, which I will define like this. So okay, so this is just the characteristic function of the positive semi-axis. So it's 0 for theta positive and 1 for theta positive and 0 for theta negative. And the rest is the same as in that omega alpha there, apart from the power. Okay, so let me remind you that although in L infinity, multiplication by a bounded function, for example, by such function, is a bounded operation in the L infinity norm, but it's not a bounded operation in the BMO norm. So in fact, this function will be in the BMO. So if I just take the function with that power, 1 minus alpha, and multiply it by the characteristic function on the positive semi-axis, in general, I will not get a function in the BMO. For that, alpha must be greater than 1. Okay? And this is why I'm writing minus alpha here rather than 1 minus alpha. So to put it differently, this function is in the BMO if and only if, again, alpha is greater than or equal to 0. Okay, so we have similar results for this function. And of course, you can write plus or minus here. This doesn't matter. So let me write plus minus plus minus. And we also have results for linear combinations of these functions. So we have results for this, for linear combinations omega alpha. Let's go A omega alpha plus A plus omega alpha plus A minus omega alpha minus. So notice that this function, although the exponent is different here, will give exactly the same rate of approximation as the omega alpha there. And so if I combine them as a linear combination, I still get the same rate of approximation. And the coefficient will be expressed in terms of this universal constant and some sort of combination of these A plus, and A minus. Okay? So this is also possible. And for more general functions, with several singularities, so several logarithmic singularities, on the unit circle. So I don't have time to describe this aspect in detail, but basically here is the situation. You can look at a function which has, let's say, 10 singularities, both at every each of these singularities, it is described by this asymptotic form. Yeah, it's a linear combination of functions of this type with different coefficients, right? So these a's will have an index running from 1 to 10, and then you will have a similar asymptotic formula for that function, where the coefficient on the right-hand side will be, again, a combination of this universal constant and all of these coefficients coming from each singularity. So there is a recipe how to combine different singularities to get the approximation of the full function. So we call this localization principle.
I wonder, when you do the approximation with the three functions, the denominators of the approximated rational functions are the same?
Unfortunately, we don't have any information about the exact rational approximation that we do. You see, we do it very indirectly through singular values of Hankel operators. So I'm afraid I don't know. Yeah, it's a very good question. How to describe exactly these rational approximations? We don't have any information. Okay. So I think I sort of described the results. Now, in the remaining time, I want to talk a little bit about the method of proof. So the method of proof, broadly speaking, consists of two components. This is the Adamyan-Arov-Krein theorem, which I will describe. The Adamyan-Arov-Krein theorem relates this topic to singular values of Hankel operators. And our second input is our previous work on singular values of Hankel operators of a certain type. And if I have time, I will talk about this as well. So let me start by just reminding you the Adamyan-Arov-Krein theorem. Once again, probably most people here know this subject better than I, but it's worth recalling this story. Okay. Okay. So first of all, let me write down the definition of a Hankel operator. So the Hankel operator, they can be introduced in many different forms. What I mean here is an operator from the Hardy space H2 to the Hardy space H2 minus, the orthogonal complement of H2 in L2. And the definition is as follows, as most of you probably know very well. So that's the definition. Okay, so you take a function, an analytic function, you multiply it by a general symbol, neither analytic nor anti-analytic in general. So then the analytic and anti-analytic components get mixed up, but then you project it onto H2 minus. So clearly from this definition, the Hankel operator depends only on the anti-analytic part of omega, because imagine if omega was analytic here, then the product omega and f is analytic, and p minus kills the whole thing. All right? So the important aspect is the matrix representation of this Hankel operator. So what is the relation with the classical Hankel matrices? Okay, so let me maybe move this up a little bit so I can manipulate this board. Okay, so if you look at the matrix representation of this operator with respect to the two standard bases NH2 and H2 minus. So in H2, these are powers of z. In H2 minus, they are negative powers of z. Then a direct calculation shows that what you get is the Fourier coefficient of omega with the index -1 minus j minus k. So what does it tell us? That the Hankel operator is unitarily equivalent to a matrix, to a Hankel matrix. Let me denote it Hj plus k. Okay, so to such matrix where Hj is just given by the Fourier coefficients of the Hankel matrix. Okay. So what I'm saying is a triviality, and it's a very well known, but nevertheless I will say it, that in Hankel operators theory, it is very important, it is very useful to shift the point of view from time to time between these two representations. So sometimes it's convenient to think of your Hankel operator as a matrix in the little L2, and sometimes it's convenient to go back to the symbol representation. So omega is called a symbol. Okay. So now let me. I want to state the Adamyan-Arov-Krein theorem, but to make it natural, let me remind you the previous two results, which are, so the first is the classical theorem of Kronecker. So this theorem says the following, that the Hankel operator is finite rank if and only if the corresponding symbol, or more precisely its anti-analytic part, is a rational function of degree n. This is a classical calculation. Then the modern theory of Hankel operators started with Nihari's theorem, which says the following, that a Hankel operator is bounded on H2 if and only if its symbol belongs to the BMO space. And this is why we're working in the BMO space. And also the norm of the Hankel operator is precisely given by the BMO norm of this anti-analytic part of the symbol. And this BMO norm here is precisely the BMO norm as I defined above, right? So it's a BMO. The norm in the BMO is the norm introduced by the duality with the Hardy space H1. Okay? Right. So now, before stating the Nihari's theorem, let me remind you the definition of singular values. They already, of course, appeared here in this conference, luckily, so I don't need to worry too much about the details. So I will just say definition. If H is a compact operator, not necessarily a Hankel operator, just general compact operator in a Hilbert space, then the nth singular value of H can be described as the infimum of H minus K, the operator norm, where K has rank n. Right? And so now I'm ready to state Adamyan-Arov-Krein theorem. Let's see, I hate to do it, but I wonder if I can fit it in this corner. Okay. Right, so So the theorem due to Adamyan-Arov-Krein in 1971 says that if H is a Hankel compact operator, then you have this description, but for K, it suffices to take only Hankel operators K. Okay? So this is the infimum of the norm H minus K. Where K is a Hankel operator. So this is a deep and rather difficult theorem. Okay. So as a consequence of this theorem, of course, directly we obtain the connection with a rational approximation. So let me write it here. Corollary. So now we take a Hankel operator, a compact Hankel operator, and we focus on its symbol omega. Let H of omega be a compact Hankel operator. Then I write down the singular value, the nth singular value of the corresponding operator. So then, according to this, I have to take this difference now. How do I get all rank n Hankel operators? According to Kroneker's theorem, I just need to take symbols from Rn. So I take H of R, where R is a rational function of degree n, and so this is the operator norm. And now, of course, according to Nihari's theorem, that operator norm can be represented as the BMO norm of the difference between omega and R. Right? So this is the infimum and then it's not difficult to see that this P minus can be removed, and what you obtain is precisely the distance in the BMO norm between P minus omega and Rn. So this is the corollary, which is also due to Adamyan-Arov-Krein. It's stated in the same paper. And this is the basis for much work on rational approximation. Okay, so it relates the distance in the BMO norm between some function and rational functions to singular values of the corresponding Hankel operator. This is what we are exploiting. Okay, so let me see. So in the remaining time, which is not much, maybe I should just say a few words about the second component of our work, which is the singular values of Hankel operators. Okay, so basically I will not need any of this. The only thing we will need is this corollary. Okay, so let me erase this part. And maybe I should make the result visible because I'm coming back to the discussion of main result. So the key point is, therefore, to analyze the Hankel operator with the symbol as appears in this theorem. Okay, so singular values of Hankel operators. Okay. So as I said, oh, it's a pity I've erased this, but I said a few minutes ago that it's important to think of a matrix representation of the corresponding Hankel operator. And this is what's going to come up. So if you look at the function omega alpha as stated there, a simple computation shows that its Fourier coefficients have the following asymptotic behavior. Okay, so we compute the leading term. This is an elementary exercise. I will not speak about the analysis of the error term because this is a slightly technical aspect of this work. And so then the result rests on this computation plus the theorem. So this is the theorem due to myself and Yafaev. And it's a result of a rather long project where we have analyzed Hankel operators with this type of asymptotic behavior of matrix entries. So let alpha be positive and let H be a sequence defined precisely by this type of asymptotic relation. Let me okay. So then the singular values of the corresponding Hankel matrix obey the following asymptotic relation. So we have Sn is some coefficient where this kappa of alpha is a close relative of that numerical constants written above. Okay. So this is the result. Now, of course, the main result can be obtained by simple combination of this Adamyan-Arov-Krein theory and this theorem. Basically, you need to split your symbol omega into analytic and anti-analytic part. You deal with them separately. This is not difficult. And then you apply this theorem. Now let me just make maybe, do I have, okay, maybe I have 1 minute, yeah? 1 minute, okay. Just two minor remarks concerning that theorem. One is that if alpha equals 0, what you get is the Hilbert matrix. Well, it's a particular example of the situation when alpha equals 0, right? So if alpha equals 0, I get 1 over j, and a Hilbert matrix is a particular example of that. And the Hilbert matrix is not compact. Not compact. This is well known. So we are right at the boundary. You see, if we try to go to the boundary of our result to alpha equals 0, we hit the situations where the singular values simply don't converge to 0. They're not defined as a sequence. Another situation is that when we started working, another remark is when we started working on this, we kind of thought we started off looking at a different type of sequence. This type of sequence where the coefficients of the Hankel matrix decay faster than the Hilbert matrix, but in the power scale, not in the logarithmic scale. So it turns out that this was the problem considered by Harold Widom in the 1960s, and he got the following result for the singular values of that matrix. So they behave exponentially. Okay, so you see, again, if you make the rate of decrease of your coefficients of the Hankel matrix larger than this, in the power scale, you hit the exponential rate of decay of the singular values. And of course, this Widom's result must be closely related to the result by Stahl, which is up on that board, because if you compute the Fourier coefficients of x to the power alpha, you get exactly, well, this kind of decay. Gamma will be recomputed in terms of that alpha. And so it's not surprising that you get exponential rate here. Although I'm not aware of somebody directly relating these two results. They were obtained roughly in the same period, maybe with 2 years, one from another. So here again, you have to go logarithmically to get better. It is compact. It is very compact. You see, the singular values decay very fast. Now, I think I should stop here. Thank you very much.